I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Igor Elkanovich from GUC and Evelyn Landman from proteanTecs. We're going to talk today about ensuring HBM reliability. So Igor, you've been packaging together a number of chips, particularly in something like a 2.5D and high bandwidth memory. Various types of that are very important for that. What sort of problems have you seen when you start putting this together?
So initially, we started to build the systems, relatively small systems with a single ASIC die for HBMs on the CoWoS platform. And the first things we addressed is standard testing to find regular faults like open short, bridge faults. And once the volume production was in the range of tens and hundreds Ks of units, the systems weren't very complex. This approach worked well, and this is a pretty much standard approach in the industry. But nowadays, the system getting much more complex. We already building products with several ASIC dies, 6 and 8 HBMs, tens, thousands of interconnects between them. And we are starting to see a second order of defects, and not just regular open shorts and bridge faults, but kind of resistive faults. And would like to address this kind of second level effects because the systems are extremely complex, very expensive. And we want to ensure it's this kind of defects to find it not just in production test environment, but also in the field, in mission mode, the defects which are developing in the field, which takes months or even years to develop. So this is a kind of challenge we came to proteanTecs, and we know the experience in reliability monitoring, and then we came to them and we tried to address together.
So Evelyn, how do we control some of this stuff? How do we find these problems ahead of time?
So the idea is to have a very small solution that can do the monitoring, but also do the monitoring while the device is working in the field. So the idea is to find something that can work in parallel while the device is working, and not stop the device to do the measurements. So that's where we came in and tried to find a very small IP that can monitor both the near end and the far end from one side of the whole system, and being very small and capable of monitoring while the device is working in real application.
So why don't we drill down into this?
So this is example of our typical system, typical interconnect between ASIC. So here you have ASIC die and HBM stack interconnected together through interposer, built on top of package substrate. And this represents micro bumps connectivity between ASICs and the silicon interposer. And you can see actual cross-section of the silicon interposer micro bumps, true silicon via, and C4 bumps here. So usually in the typical chip, we have hundreds of thousands of such micro bumps. But most of micro bumps in the system, we usually double or triple or multiple every connection to make sure that failure of every microbump will not cause the failure of the system. The only place when we have very dense connectivity is the connectivity between ASIC and HBM. And in this place, we just don't have enough space to double connectivity. So every interconnect have only single die, single microbump. And the only way we can do, we use several redundant lanes to replace the failing ones. So the first solution we developed, and this is pretty standard, to look for standard open or short faults and to replace them with redundant lanes.
So Evelyn, from your side, what are you seeing? When do you notice something's wrong?
So we are continuously monitoring in a way the resistance being seen from the PHY side of where the ASIC resides, both from the near end and the far end of the connectivity. And we see both the whole trace from the bump, the trace itself, and the other bump, and we are monitoring the changes in time. So the solution is not only an IP, but it's a analytics platform that is getting the IP's data out of from the chip into a software platform that is monitoring the changes in time, and then when the changes start to get close to some threshold, then we can apply alert and ask for a predictive maintenance a request, because this means that in a very short time this connectivity may fail.
And Igor, from your side, as you get to an interposer, you potentially have tens of thousands of through silicon vias that you have to align here. And not all of them are necessarily, because of process variation, printed exactly the same way all the time. What does that mean for reliability from your side?
Yeah, maybe this picture explains better exactly as Evelyn explained, and to address your question. So as you said, we had tens of thousands signals interconnecting HBM and our PHY, and every signal has slightly different shape and slightly different signal. And our IP is pretty much robust to address different shapes of the signal. And even if the signal waveform is degrading, we have enough margins to accommodate this signal. But for instance, in this slide, you can see that certain signal quality is degrading a bit because of different resistance events building up in the system. And this is, by the way, represent the mission mode, the normal operation of the chip. What proteanTecs agent helps us, they constantly monitor quality of every pin, every bit. And once they see abnormal closing of the signal, of certain signal, even the system is still operating very well because our PHY has sufficient margin. But this trend is probably represents a certain physical problem developing in the system. Once they report to the system this problem and this dangerous trend, so the system, first of all, the system can monitor this signal and can monitor this trend to see if it's getting worse and worse with the time. And the second, the system can take decision that in the next maintenance cycle, they can replace this signal with redundant one. And then to prevent failure once this physical defect will develop into the real problem. And once it develops to the real problem, the margins of RFIs will be not sufficient to accommodate this signal anymore.
Evelyn, from your standpoint, there's a lot of different use cases that are possible here, and each one of those potentially can highlight something different. How do you go through and say, this is normal, this is not normal, we haven't seen this before? How do you set those parameters?
So we do this continuous monitoring. We have enough sensitivity to see very, very small changes, which may be not a real problem, but when you start monitoring time, you see the trend. So once the trend is going in a way that you see the resistance starts to increase 1 month after the other, we can really decide this is not a false positive. It's really something that is getting close to where the system won't have enough margin, so we have enough time to give an alert that something is building here, and better take it in the next cycle to repair it before it fails.
So do you have to combine that with domain knowledge about what you're actually doing there? Because you are continuously monitoring these systems. Is it now important to say, okay, we understand that this is a problem, this is not a problem?
Yeah, so this need of domain knowledge, but also remember this is real data, so it's not trying to guess from some circumstantial measurement. Let's say if you are measuring temperature, you may say if the temperature is changing, maybe something will happen. But maybe yes, maybe not. But here this is a real measurement, so it's much easier to predict what is going to happen when you have a real measurement and you have correlation. When the resistance gets to a given value, then the system will get out of margin. So it requires knowledge, but still it's easier when you have a real measurement from the system.
And Igor, most of the 2.5D chips have been developed because you can't really get the benefits of power and performance out of scaling anymore. So now you have to move to these most advanced nodes, but you also have to put them together into new architectures in order to reap those kinds of benefits. So you're now dealing with not only the packaging effects, but you're also dealing with these advanced chip effects as well, the physical effects, the electromagnetic interference, all the different challenges that you've got going on there as well, right?
Right. First, we developed our first technology. It was still 16 nanometer, then 7 nanometer. Recently, we already have our 5 nanometer. Every technology brings their own challenge. Another challenge is the speed. So the first device we developed with 2 gigabit per second. Now we're already developing, and now we already have in the lab 3.2 gig. And now we are developing 7.2 gig. So the scale and everything I described is just in 2-3 years. The process change, the amount of chips, the amount of connectivity, the speed. What is one impressive point in proteanTecs IP, that it's very small, it's extremely small and very low power, because here we need to accommodate thousands of these IPs, thousands of small monitors for every pin we need to accommodate. And this technology is easily ported from process to process. First, they developed it for 7 nanometer. Now then they developed for 5 nanometer. We are already together developing it for 7.2 gigabit per second HBM3 technology. So the monitoring is itself is pretty much is very efficient and easily ported from process to process. And this is very important for GUC to keep this scale of speed, process, and the size of the system to keep the space and to keep this technology in this space.
And Evelyn, from your standpoint, does it matter if it's going from 16 nanometers all the way down to 5 or 3 nanometers? Is it the same signals that you're measuring?
It is more or less the same. Of course, we need to characterize everything. It's not exactly the same, but yes, it's more or less the same thing. Although we, of course, need to do all the simulations and check everything once again.
So assuming with HBM you do come up with a problem, what can you do to fix it?
So we have these redundant lanes. In the first system, once we found the problem in production test, we found the open or short faults or bridge faults. We were replaced them in the redundant lanes. But nowadays we did next step. So we are able to fix systems not just in production stage, but also in the field. In the normal operation, if we see this trend, then we can actually replace by software. We replace this lane by redundant lanes. We burn this information in ifuse. So in the next boot cycle, the system will automatically use redundant lane instead of the problematic lane. And this allows us to extend life cycle of these products to allow no interruption of operation. Think about this system are very playing key roles in the customer data center. This product is networking, or this product is AI. And any failure of HBM bit can cause the failure of this product, and the replacement, this is very expensive cycle. So by this system, we are preventing this failure. We are monitoring this problematic trend before it's actually happened. And then in the next maintenance cycle, in the next boot operation, we just replace this lane. We burn this information in ifuse. So in the every next boot cycle, it will automatically use redundant lane instead of problematic one.
So Evelyn,
yeah.
Do we now see any variation in this at all, or is everything still exactly the same as it was? And do we need to establish a new baseline for the how the data is being moved through?
No, so we don't need to establish a new baseline. We continue monitoring. Of course, if there was one lane that was problematic, we will start after the maintenance cycle. We will see it coming back into a normal place. But from the analytics point of view, it's only okay. Now the alert is gone and the problem is gone, and now we start from the beginning. So there's no need to tune anything. It's just seeing, okay, the problem has disappeared and now it looks normal once again. So
obviously you've tested this out. What have you actually found?
I can show it in the next slide. So first, we measure, this technology is already implemented in GUC's HBM test chips, both 7 nanometer and 5 nanometer. Here you can see example of 7 nanometer test chip measurements. The sensitivity of what we call near-end microbump resistance and far-end microbump. This is different microbumps under the ASIC die or HBM die. Normally, in normal system, the resistance is very close to 0 ohm connectivity, and this implies good signal quality. But you can see that once resistance is developing, the parasitic resistance, we can easily monitor it, and the proteanTecs system can report the growing resistance. Actually, this resistance, you can see, is still not very big. It's like in the range of 10, 20 ohm, which means that signal quality is still be good. Even in this range, our PHY has sufficient margins to operate in this range. But you can see that proteanTecs monitor can already recognize the trend, and this can give us insight to take the action to replace this problematic lane.
So what happens with the outliers and all this, which is always one of the key metrics for what you're trying to find?
Yeah, so maybe we can see in the next slide we have an example for things that are also being seen during test. In some cases, not all the channels and the bumps look exactly the same, even at time zero. So also this technology can be used to find outliers. Here we see an example of some outliers being found. And this also can be used to improve even better the DPPM from the beginning, but also to take into account that maybe these outliers are going to need to be specially monitored because they may degrade faster than the others.
So this gets significantly harder from here. I mean, as we move down into 5 nanometers, 3 nanometers, as we start packaging together more things, it becomes more complicated. What do you have to do next? What sort of challenges are coming down?
The next challenge we already started to address together, actually in 2 directions. In HBM direction, the next generation of memory called HBM3, which takes the speed even to higher speed to 6.4 and 7.2 giga, and it requires a very different approach for monitoring, much more sensitivity. The speed is challenging. The signal level is also very small. And this is one direction we are developing together, this monitoring. Another direction, GUC is developing the new type of interface. We call it G-Link, which is used for both 2.5D integration of dice and stacked dice, 3D integration of dice. So we are starting to work with proteanTecs how to address signal quality monitoring of these IPs. These IPs comes with even higher challenges because we want to achieve 16 gigabit per second, 3D even higher, bigger challenge. So this is a next technology, but the idea that the whole we are building enormous systems with 2.5 and 3D integration, and the connectivity quality monitoring in the field and mission mode. This is a critical issue we'd like to address together.
Yeah, so as Igor said, the challenges never end. So yes, we'll continue to work together. Both HBM3 is going to be very challenging, and it looks like it's going to be very used in the industry. But also this trend of die-to-die connectivity is coming very fast. Once again, because people want to do very big devices, so they need to divide it into different chips, or want to use different technologies, and not always go forward in the technology in some cases. So this new trend is coming. It was being talked for a lot of time, but now it's coming in. And so we are starting to work with the GUC also in this direction, which is very interesting for us and important for us.
Igor Elkanovich and Evelyn Landman, thanks for a great explanation.
Thank you very much.
Thank you, Ed.